Hello, I don't know if you can hear me.
Yeah, hi, hello. Can you hear us?
Yep, perfect. Sorry, I'm at the airport.
All good. We're just waiting on Dr. Kim. And I'd say if we're, yeah, I give him a call. But
Yes, he emailed me, he will be.
so.
Okay, sounds good.
I almost like that. So this seems good.
I'll take your word for it.
Yeah, 12 what if the content is really the same.
Yeah, I did that stuff.
Oh, you had some.
Just get started. And also
Sounds good. Mine is especially when I'm working and driving.
All right, good morning, everybody. I'm Mario Mata. No, just kidding. But I want to give just a couple of opening remarks to introduce Mario. This is just a little small tradition that my PhD advisor used to do, and I believe her PhD advisor used to do. So I'm trying to continue that, but basically we start by mild embarrassment of this is the very first exchange we've had, I believe. This is from January of 2018, and actually Mario reached out to my my PhD advisor because he was interested in my work that I published a few years ago, specifically about electric field enhanced surfactant, enhanced boiling. Something extremely specific, and so it was kind of like, okay, well, what kind of power supply were you using? What was the amps? What was that voltage range? So we're immediately talking shop, and like, who is this guy that like cares so much about the details of my? Is he questioning my work or whatever, right? So, but anyway, I gave him a very detailed response, because you're always really cautious about these things. Also, interestingly, he addresses me as Dear Jeremy, as I prefer to be called, So cool, yeah, and everything, okay. At the time, I was not at UNLV. At the time, I was a postdoc at Princeton. And then the next thing I know is, wow, he's really nice. He's like very courteous, right? Thank you for your kind of support. He really, at the time he was at National Taiwan University, and so he wanted to sort of his voice there. Then like a year, I guess, a year and a half later, I get an email. Now, dear Dr. Jeremy Cho, what changed? I didn't even arrive at UNLV at the time. I had just accepted the offer, and I think I was like, I didn't move to Las Vegas, and he emailed me like, "Hey, I heard you're appointed. Do you have any openings?" So I was very lucky to say that I was like my first international recruited student, but I didn't really do any recruiting. He came to me. So I'm like, sure, yeah, let's like make this happen. And so I think about it, a half a year later, Mario was able to come out. And immediately what I noticed about Mario is that extremely organized person. I don't know if any of you dealt with communications with him or I just done a lot of things. He always sends these very nice detailed emails, different steps, and sending notes to myself. So he's really good at that upward management. And then he created this beautiful bill of materials template for us to use in the lab, and all you other lab members, please use this template, right? Instead of just randomly putting stuff in Slack, please follow Mario's example here. And then also he's just been a great spirit, in the lab, a congenial spirit, and so friendly, always happy to help. And if you notice, if you look at all the lab pictures, you know, a good portion of them are selfies. And Mara is the biggest picture because he's always the first one to grab up. You know, a really dedicated individual just to research and everything we do for the lab. So I'm really excited for you guys to see what he has to share for you guys. Thank you, Jeremy. Thank you.
Kim will join remotely. So
Okay, sounds good. Thank
I
you.
forgot about it.
So now let me share my slides. It's fine. All right. Good morning, everyone. Welcome. Thank you for being here. I'm very excited to see so many familiar faces, specifically my committee members for allocating time to be here and also attending through Zoom. My lab members, friends, and people that I know that have been coming through the summers. Michelle, thank you for for being here. And my family, special guests that they are watching through the camera. And later on, I will have to use some translation to explain what's going on. Right. This has been a very interesting journey for me, putting things together, crafting this work for the past 4 years and a half. It wasn't until I started preparing this that I realized that this journey not only is for the sake of science, but it's all about people. And this is a journey that I have been enjoying very, very much here at UNLV. And I really appreciate Dr. Cho for all his unwavering support and his patience as well, because there are times that I might be a little stubborn, and he has been very patient in that regard. Okay, so now let me move on the technical aspects of my presentation, where I disclose how I improve boiling heat transfer performance with chemical additives such as surfactants. So let me walk you through this research that I have been conducting, starting with boiling. Boiling is a heat transfer process very effective to remove heat from one place to another. Once the liquid turns into the vapor, can carry large amounts of heat. Here, if you see this spot here, you will see that boiling is chaotic, and you see a lot of bubbles being generated here. These bubbles are, of course, in slow motion for you to perceive, this very dynamic behavior. Once heat diffuses to a material, and that material contains some liquid, in this case, let's say if it's water, then that fluid will turn, once you reach the saturation temperature of the liquid, then bubbles can form because the vapor pressure inside those bubbles is equal to the atmospheric pressure, and therefore you can release that heat to the ambient air. So boiling is extremely important and ubiquitous because you can find boiling in so many industrial and commercial applications, such as nuclear power plants, desalination centers, for avionic components, electronics, or even the HVAC system of this building. To better understand what is boiling, let me walk you through the full boiling curve of water. We have here a full boiling curve of water having the heat flux versus the superheat. This superheat is a difference in temperature, the temperature of the surface and the bulk solution or the fluid. So boiling is characterized by typically by four boiling regimes. The first regime, we have natural convection, where you add heat to the surface, vapor bubbles are not formed, and the temperature difference here in the superheat is very minimal. But as you keep supplying heat to your source, then you reach the onset of nuclear boiling. This is where you start seeing bubbles, and this regime is extremely important for many technical applications. So this green area is where we start seeing nuclear boiling. But if you keep supplying that heat, then you will reach the critical heat flux. So this is the maximum of heat that the system can hold before burnout. So after that transition, there's a rapid transition in the how bubbles will form, having this entrapment of bubbles that they make an insulation layer on the surface, so heat is not that effective as in the nuclear boiling regime. So you want to prevent this transition, so we need to understand how to effectively modify the boiling curve or to understand what's happening in these regimes. In my research, I mainly focus on this regime because I don't want to transition into transition film boiling. So the results you will see through these objectives in my dissertation are mainly of all the boiling curve of water up to the CHF, which is the critical heat flux. Okay, so how can we improve boiling? There are many approaches that we can take for improving boiling heat transfer. One of the most common approaches is using passive technical techniques that you can use, such as surface modifications with micro and nanostructures or microporous materials. So what these modifications are doing, they are changing how bubbles form, how the surface of the material also has a different wettability properties, so also affecting the overall boiling heat transfer performance. Another very interesting avenue to do that, to improve boiling, is with chemical additives, such as surfactants. So surfactants, once you add them in the liquid, they will alter the interfacial property of the liquid and therefore have an impact on the boiling performance. So what is a surfactant? A surfactant is a molecule, it's a monomer that it's amphiphilic, has a hydrophilic head, wants to stay on the side of the water, and the hydrophobic tail, which wants to repel the water. It's on the other side, on the vapor side, or in the air side. So a surfactant, it has a structure, a chemical structure of this type. Depending on the surfactant, you will have a different head size, and also the tail length might be accordingly depending on the chain groups of how many carbons you have in the tail. Surfactants have different types. We have surfactants have no charge, like the non-ionic, and we have surfactants with a charge, might be ionic surfactants. So maybe you might be unfamiliar what is a surfactant. A surfactant is the main component of many detergents. Detergents such as shampoos, or for dish soaps, and also different materials such for insulating foaming agents to insulate these walls, or even for firefighter mitigation. Surfactants has this very unique property called the CMC, the critical micelle concentration. Once you add surfactants in the liquid, they will dissolve, and there you keep increasing the concentration. Surfactants will absorb to the interfaces, and once the interfaces are full, we have gamma EQ, which is the equilibrium surface concentration. But remember, we are increasing the concentration. There is no space for the surfactants to absorb to the interfaces. So surfactant monomers will aggregate and form micelles. So surfactants have this effect on the, once you add them in liquid, they will alter the interfacial properties of the liquid. How can we quantify that? The way how we quantify those changes is with the surface tension and the surface concentration. The surface tension, I can take this viscosity equation, which can help me to evaluate how much that surface tension is changing as we increase the molar concentration. As we increase the molar concentration, surfactants are known to decrease the surface tension. And that's because there's an increase of surfactants diffusing to the interfaces, so you have more surfactants. And there's a point where you reach the CMC, which is the equilibrium. It's an equilibrium property. So once you reach that state, we plateau here, and then there is no more changes on the surface tension because there is no more surfactants absorbing to the interfaces. The way how we quantify this is with the Lehmer isotherm. So surfactants, what are surfactants doing to boiling heat transfer? So now that we have a sense of what is a surfactant, what they are doing to the interfaces, what happens when they absorb, for example, in a case like this, you have a vapor bubble, you have a solid. So what's happening here? So very interestingly, my academic advisor, Jeremy Cho, a little over 10 years ago, he saw that when you look at the heat flux over the superheat, you have a boiling curve of water, which is the black line. There is no surfactant added, but as you increase the concentration, there's a shift in the boiling curve. So we are modifying the boiling heat transfer. the way how we quantify that is with the heat transfer coefficient, which is the ratio of the heat flux over the difference on the superheat. We have the surface of the temperature minus the saturation temperature of the fluid. Now we have the critical heat flux, the CHF, which is the maximum amount of heat that can be supplied through the system. So here the mission is to identify how this boiling curve is shifting. So when you have surfactants in boiling water, you will see changes in the boiling behavior. When you boil water with no surfactants, you see a larger natural size of bubbles here with no surfactant additives. But when you increase the concentration with surfactants, surfactants tend to decrease the size of the bubbles and promote more nucleation sites. Quantifying boiling heat transfer, we know that the boiling curve will shift to the left, but what about the CHF? So the CHF, the critical heat flux, for many surfactants, it will decrease. So now we have some knowledge that surfactants have an HTC CHF trade-off behavior. In the following slides that you will see, instead of saying HTC, I will say R or RHTC, which is the relative heat transfer coefficient, which is basically a ratio, the HTC of the surfactant over the HTC of water. And similarly for the CHF, we have a ratio of the CHF of surfactant over the water. So now looking at what people have been doing over the years when they are adding surfactants in boiling water, we were very curious and we were thinking, okay, let's see what people have been doing. They have been testing surfactants either in a single test, maybe it's only one surfactant or 5 different surfactants. But the interesting thing here is that these tests were carried out at concentrations that are close or near their CMC. So this is kind of like we were questioning ourselves, why is that? Why these tests are being tested close to their CMC? So this literature suggests that once you increase the molar concentration, conventional wisdom will say that once you reach the CMCs, you will reach the peaks on the boiling performance. So this is setting a new avenue where surfactants will behave in their optimal peaks when they are close to the CMC. But now we have some doubts here. Let's think about boiling. Boiling is a very chaotic and dynamic process. But CMC is an equilibrium property. The question here is how these two things, when you have a very dynamic system, but you have an equilibrium property, how can they equate? How is that even possible that you can reach optimal peaks of enhancement at CMC? For this reason, I want to present the objective number 1 of my dissertation. This objective 1 encouraged me to test a wide range of concentrations with different surfactants. Because remember, those conventional wisdom studies are testing surfactants close to their CMCs. So we wanted to expand the scope and go beyond that. Concentrations that might be way below the CMC or way above that CMC. In this first objective, we were limited in how much our boiling setup can operate. We only identified HTC. In the second objective, we want to dive a little more into details what's actually happening at the interfaces. Is there a way how we can quantify what's happening to the boiling behavior? And not only we can quantify HTC, but we can also quantify CHF. So now, unifying this groundbreaking work and knowing that, okay, we have some concentration range, we have tested different surfactants, we might have a way how to explain what's happening. We want to combine all this knowledge, but it's a very narrow concentration, but for many other types of surfactants, perhaps surfactants we haven't even tested here in the previous years. So objective 3 wants to identify that. And with this objective, we want to find a way if there is perhaps a way we can unify all these findings and disclose general correlations that can quantify boiling enhancement for aqueous surfactant of any type. The first leg of my research was conducted when I came to UNLV in 2020, And it was a beautiful transition to understand all the theories, all these beautiful and complex field of boiling with surfactants. And that's, we have our first publication on scientific reports. Then since 2022, then until last year, I was so invested into objective number 2. And there we have a new paper that is under revision. And then since last year until now, I was working objective number 3. And combining all these things, that's what I want to show you the journey of my dissertation. Now let's move on to objective number 1. Let's have a look at this chalice, right? You see that a chalice typically have like a big opening, then narrows down at the center, and then have a different shape at the bottom. So looking into this, we want to address this in this manner. Starting like testing a wide concentration of, in the molar concentration, testing a wide range of surfactants, and then narrow down my attention what's actually happening at the interfaces. And there I describe this with the diffusion of surfactants. Combine these two understanding of what's happening, I want to finish strong with general correlations. So now let's move on the top part of the chart. Objective number 1. In objective number 1, I have 5 different surfactants. 2 surfactants are non-ionic, have no charge, and 3 different surfactants with they have a negative charge. These surfactants, I illustrating a very simple way what is the structure, a very simple way of the structure of these surfactants. What I'm showing here, it's how many carbons are in their tail. So if you see a different size here, these surfactants are typically in the same order of magnitude in the dentlets, but these surfactants are of different type. If you see a surfactant, for example, S14S, these 14 means there are 14 carbons in their tail. And for twins, it's a little different, because this 40 doesn't represent 40 carbons. In this, for this surfactant, there are 16 carbons in the tail. So what I'm showing you here is just a very simplistic illustration that surfactants have different sizes. How did I conduct this test? Okay, and the first year I was, designing, and we were building our first boiler in our lab. So this boiler has a vertical orientation heater, like in this way. So we do our analysis in this region. With this beautiful mini boiler, because compared to the next boiler I will show you, the size are very, very different. So that's why I'm using this boiler as a mini boiler. And this is a control area in our lab. So with this mini boiler, we were able to conduct over 150 experiments just for the sake of the publication. But that mini boiler, I bet, survived more than 500 experiments. With this system, we have here a direct illustration, a direct picture of the boiler. So you see a copper tube, and we record the boiling events with a camera. And remember here, this is a vertical orientation, and it's a copper material. So going back to what people have been exploring close to their CMCs, in our work, we take a step a little farther. What we did here is we took the 5 different surfactants over the largest testable concentration range up to that date, and these surfactants span many orders of magnitude in their CMCs. Surprisingly, if we follow what conventional wisdom has said, then we should be expect that the peaks of these curves of the RHTC versus molar concentration, they should be peaking at their CMCs. But what we see here is something different. They are not peaking at their CMCs. They are reaching their optimal RHTCs in a different concentration, something we call the unified universal concentration range, which is something about in the range of 1 to 10 moles per meter cube. Therefore, with these findings, we have evidence that conventional wisdom is wrong. How can we explain this? What is happening at the interfaces is that at low concentrations, there is a small amount of surfactants absorbing, so therefore there are less nucleation sites and your HTC, your boiling performance is low. But as we increase that concentration, you should be expecting more surfactants diffusing to the interfaces, you should be expecting more nucleation sites, and you should be expecting an increase in the HTC. A way how I can explain this, how can I explain this roller coaster behavior where everything goes up but cannot keep going on forever, right? So we reach a peak in this universal concentration range, but also there is a decrease. And let me explain you why is that. The reason we have this increment in the RHTC is because that dynamic absorption. That dynamic absorption of these surfactants absorbed into interfaces. We quantify that with the characteristic timescale of diffusion, the T sub diff. So we have gamma max, which is a theoretical maximum concentration of how many surfactants are allowed at the interface. We can predict from theory, and also the diffusion coefficient, that these two variables do not change many orders of magnitude from surfactant to surfactant. So what is changing here is C, the molar concentration. This characteristic timescale diffusion is highly dependent on changes on C. As we increase the molar concentration, we have a higher HTC, and this degradation in RHTC is because there are, in both solution, there is an increase in viscosity. Remember, at higher concentrations, interfaces are full, so surfactants are having different effects, like critical shear forces, bubbles having a difficult time to depart, so that's affecting the overall viscosity of the fluid. And this can be also very explained with the well-known Rosenthal correlation. Well, it can infer that the HTC is proportional to the inverse square of the viscosity. So now, I want you to pay attention to two competing timescales. We have two timescales that can give us a very intuition of what's happening. And this information will be crucial with what I will present in objective number 2. We have two timescales, bubble lifetime. For a typical bubble lifetime in boiling conditions, the bubble that the time it takes for a bubble to grow and before departure, it's about 20 milliseconds. Now, we can calculate diffusion timescales, and if we take a rate of that, if the rate is below 1, we say that the diffusion is slow. There is a small amount of surfactants diffused into the interfaces. But if that rate is close to 1, it's where you should be expecting the optimal peaks in RHTC. On the other hand, if that diffusion is higher than 1, that means that diffusion is fast. We have the interface is full, so that's having a big impact on the overall boiling performance. With this, I would like to close the chapter of the objective number 1 by summarizing that we have this unified concentration range that occurs for any type of surfactant from 1 to 10 millimoles per meter cube. And this HTC enhancement is due to a dynamic absorption of surfactants, and it degrades due to increments in the viscosity. And the amount of the absorbed surfactant to the interfaces is happening within a finite time window of the bubble lifetime, and this is a diffusion transport limited behavior. With this, I close how we identify a concentration range, gave you some insights why the HTC is increasing, why the HTC is decreasing. But remember, I'm talking about HTC. Now I want to show you what happens to the CHF, the critical heat flux. With this system, we were limited on how much heat we can supply. Otherwise, our system will not sustain those large amounts of heat. We needed to design a new equipment. And also, very importantly, objective 2 wants to address how surfactants are actually changing boiling behavior, how surfactants are changing the impact on the overall boiling heat transfer performance. So now that we know the concentration, we want to know our concentration. We don't need to explore, we are knowing the unknown. Now we want to explore concentrations where we know we should be expecting enhancement with surfactants. We take 3 different surfactants, different CMCs, different chain lengths, but they are of the same type. They don't have any charge in the head. We don't want any effects that might be created with having ionic liquids. So in this case, we have non-ionic surfactants. Now we have a way different system here. We have a big boiler. If you remember mini boiler and now this one, there's slight changes in what you perceive and the amount of components. With this boiler, we can, this copper rod here has encrusted 8 different heaters and can supply enough heat to create the conditions that we want. The conditions are that we want to reach CHF. A very interesting characteristic of this boiler, okay, I want to show you the controls area is the same controls area, but the difference is that we have this boiler, instead of being on this side, now we have it on this side. So my head was always shifting whether it was here or here. It was an interesting 4 years and a half of, doing like this. So the difference of this boiler, you see a flat surface now, and we have a gold surface. Well, why we chose that? The reason we have a gold material is because we want to minimize corrosion-induced changes on the surface that are created when a metal it's exposed to water. So we minimize corrosion on our gold sample, which we actually quantify and we measure, and it's very, very minimal over many cycles of the experiments. So we wanted to focus on our experiments with surfactants. And here I'm just depicting a quick video of what's actually happening when you see CHF. You see these very big bubbles creating on the surface, carrying a lot of heat. So we have to have a very controlled system to do that. So now let's take these 3 different surfactants. Okay. Let's throw them in water. Let's test them at different concentrations. If we listen conventional wisdom, we should be expecting some different changes at the respective CMCs, right? Or what I want to show you next, we saw something different. This is the first piece of evidence that this is something independent of the CMC. We have 3 surfactants. As we increase the concentration, we see synchronous, similar changes in the bubbling behavior for these 3 different surfactants. They are not having different bubbling behavior at their CMCs. So this is evidence that CMC is not important. There is something else that can explain this. Recalling the computed timescales, we have that if this TDIF is bigger than the bubble lifetime, we know that that ratio is lower than 1, meaning that the fusion is slow. Coincides with what we found in objective number 1. Now, if we get closer to 1, a molar concentration where we should be expecting some changes, in fact, now we are visualizing that there's evidence that bubbling behavior starts changing around this concentration. But if we go to higher concentrations, we should be expecting a very fast diffusion because the ratio is bigger than 1. So we see similar bubbling behavior at the same molar concentrations. As we increase the concentration, we should be expecting the size of the bubble reducing, more frequency, more nucleation sites, and also the non-color sense effects, how bubbles, whether they merge or not merge, is also increased, which is another interesting characteristic of surfactants, that they want to prevent bubbles from merging with each other. So what about experimental data? I want to show you, okay, we have visualization here, right? We have some snapshots, but I want to give you another piece of evidence. Experimental data we can quantify with the HTC and CHF. Looking back again to a boiling curve of water, HTC over superheat, we see that increments in the concentration will have major effects on how your boiling curves will shift. We increase the molar concentration, we see that HTC, in fact, yes, indeed increases, but CHF decreases, right? If you remember the HTC-CHF trade-off behavior, we validate that here. And the way how we quantify diffusion now is not approximate, but it's equal to this where we plug in the Lamor isotherm. The KL is the Lamor constant that we can also calculate from experimental surface tension data. And we have an accurate way to calculate, diffusion. So we see that these increments in the diffusion rate are governing what's actually happening in the boiling dynamics, and that the HTCHF trade-off behavior exists. So now we have visualization, we have experimental data. What else might be missing, or what else can we add to make this very compelling? To tell you that CMC is not important. So perhaps have a different way to quantify dynamic absorption for different scenarios. So we have a direct modeling of the dynamic absorption using the word-to-die equation. With the word-to-die equation, which is also highly dependent on C, which is the concentration, we non-dimensionalize this for simplicity, plug in the Lamor isotherm, and this allows to plot the dynamic absorption versus the molar concentration. Now here, I want you to pay attention to the hard lines at the center, because those are the ones for a typical bubble lifetime of 20 milliseconds, perhaps, atmospheric conditions, as how I'm testing in our lab. When we increase the molar concentration and we reach 0.5, that means that translates that the interfaces have full. But if we keep increasing that concentration, we reach a maximum of like surfactant flow absorbed to the interface, and we will reach that we will get a case like this where the interfaces are in plateau, and then you don't see any no longer increase. But what happens if we model this for different conditions? Conditions like, what if someone asks me, okay, Mario, is this true actually happening for bubbles that are of a smaller size? Perhaps bubbles that only have a lifetime of 1 millisecond. Where do you encounter this? In systems that you might increase the pressure, in pressurized systems that will hinder the size of the bubble, so you will have a smaller bubble, so therefore also the quantity of surfactants, the amount of surfactants diffusing will also be shifted. So if we model that, we see the dotted lines here, we see that in fact the pattern is the same. We see, but what we see here at the same concentration here compared to B2 in B1, we have that at the same concentration, the interface that we say the interface is 10% full. So we just see a shift into that, but it corresponds to a similar behavior. So what about conditions like a vacuum, where the bubbles have a longer lifetime to grow? Therefore, you have infinite time for the surfactants to diffuse to the interfaces. We see that it follows an interesting pattern here, and something that I would like to perhaps test in the future, or leave it this as a future suggestion. So what I want to show in this plot to show you how powerful is the word-to-die equation, and also that the word-to-die equation is backing us, explaining what's happening with dynamic absorption. Now let's put everything together, and away how I want to finish in the last two slides this objective number 2. We have dynamic absorption, we have also body enhancement quantified with the HTC, and we also have boiling crisis, which is quantified with the CHF. If we put all these together, we see some remarkable results here. We see that yes, diffusion is slow. We shouldn't expect any changes in the boiling performance, but when diffusion is fast, we have synchronous changes, because there's a higher dynamic absorption. As we increase the molar concentration, HTC also increases. And because of that, CHF decreases, because surfactants are diffusing to interfaces, and this is a concentration where you should be expecting those changes. And that is regardless of the surfactant type. And this is driven by the equation that I showed you before, where we have plugging the Lamor isotherm. So now, if someone asks me, okay, Mario, you show me very cool data. How can you validate that? Is there a way how we can test this, maybe in a different equipment, just to to confirm that that's actually happening? Well, we have one of our collaborators in Slovenia. He has a different boiler. That boiling surface is different. So there are also different conditions with what we are testing here in the US and what is being tested in Slovenia. And we saw that combining these two results, the results of our collaborator follow the similar pattern. A small diffusion, it doesn't see major changes, but when diffusion is faster, surfactants absorb into the interfaces, then there is also a drop in the CHF, which is very remarkable. And then I want to thank Professor Mathis Mosset for his contributions and making this work very to validate our results. So now with this, I would like to close objective number 2, where I show you that changes in bubbling behavior are synchronous with the concentration, with changes in the concentration. And this is a molar concentration dependent diffusion of surfactants because of that C. And that is governed by 2 comparative timescales. We have the bubble lifetime and we have the characteristic timescale of diffusion. And the boiling HTC CHF trade-off behavior prevails in aqueous surfactants, regardless of the surfactant type. So now, before moving to objective number 3, a quick summary of these 2 objectives. We know the concentration, we know what type of surfactants we have been testing, but there is something missing. We want to know if these will also prevail for other types of surfactants. Perhaps surfactants have a positive charge here. So we have tested surfactants with no charge and surfactants with a negatively charged surfactant. But to do that, we have to recreate a slightly different conditions. And also, very importantly, we want to unify these results and to see if there's a way how we can put things together and have general correlations that could quantify body enhancements for any type of surfactants. Or surfactants perhaps hasn't been tested, or we could predict with some correlations. So now, objective number 3. I don't want to name every single surfactant because this work covers so many surfactants. We have 9 different surfactants. The first surfactants, we have the amine chloride. They are cationic, they're positively charged surfactants. They are also known as ionic liquid-based surfactants. We also have the sodium sulfate family surfactants. They are anionic, and we have a single twin 40 ionic surfactant, non-ionic surfactant. So we take these surfactants, and because I want to show you how the chain length changes, you see that this surfactant C2 means there are 2 carbons. That number 2 means that there are only 2 carbons, so this is a shorter, a small short chain length surfactant. But that thing means the surfactant has a longer tail. And similarly, with the sodium sulfates, we have surfactants of comparable size, and we have a surfactant of very long chain length. In this, I want to quickly show you the properties of the surfactants. Because of those changes in the chain length, also they exhibit a different CMC. So you see, we are testing surfactants that are no longer just in a limited concentration, in a limited CMC range, but we are testing surfactants that are far, far away from what we have tested. So we want to unify our results with this other type of surfactants. The cationic surfactants, as I mentioned, they are also known as ILBS, and they are from the methyl imidazolium amine halide family, meaning that the meme refers to the methyl imidazolium, and the halide part of the cation is the chloride. And we have the sodium sulfates, and all these surfactants I have described them from the long chain surfactant. They are lower mid CMC levels. You can see, just taking a sneak peek here from the table, you see that the CMC of C10 meme CL, it's about 40 moles per meter cube. But if you take, on the other hand, like C2 meme CL, it's something way about 1,000 moles per meter cube. That's concentrations way higher to what we can test in our boiling conditions, in our boiling setup. So with these surfactants, we want to see if they also comply with this HTC-CHF trade-off behavior. Remember, we increase the concentration, you should be expecting higher concentration at the interfaces, so should be having an impact on the overall boiling performance, increasing the HTC, increasing the CHF. And that's because it's causing the results in the bubble dynamics. The picture that you saw how bubble was changing, the bubbles are becoming smaller, there are more nucleation sites, and that's affecting also a rapid frequency as you increase that concentration. Very interestingly, we have seen reports that similarly might breaking this behavior. The behavior we have seen with surfactants where, HTC increases and CHF decreases. We have seen surfactants studies that are proposing different findings where you have, on the other hand, HTC decreasing as you increase the concentration, or you might have other results where might be increasing the CHF, which is very interesting to us because we have seeing a specific partner. So we wanted to see if this will comply with all these surfactants that we have tested. To do that, we needed to modify our existing boiling setup. So we wanted to apply an electric field to have a well-controlled environment of the absorption distortion mechanism with surfactants that electrical positively charged in the heads. So we apply a counter electrode of titanium. So we can, I just wanted to show you this beautiful contrast area picture. It's dark because it's midnight. That's the perfect time to do experiments. If you do experimental research, you will know that's a beautiful time when it's pretty quiet and it's a beautiful moment to do your work. And once we adapted this kind of electrode, this is what it looks like when it's already assembled. So with this, we have an initial hypothesis here. We have surfactants that we wanted to know what's happening. How is that perhaps possible that you can increase the CHF? So we were thinking, well, I was discussing with Jeremy after so many sessions, and we were like, oh, maybe it's the cation, like maybe it's absorbing to the interface and doing something that surfactants should not be doing. But maybe it's that part of these specific ionic liquids, surfactants, ionic liquid-based surfactants that might be doing something different. And that's when you don't have any control environment of your surface, because most metals have a positively charged surface, so that will attract the cations. So we wanted to test that, whether it was that or maybe some deposition effect that I was breaking the CHF trade-off behavior. So to do that, we were also thinking some theories, the inner stellar layer. We wanted to narrow down into that. We wanted to explore the diffusion double layer. But when we did our experiments, okay, we saw nothing. We were applying electric fields, and that was nothing. We very different electric fields. We went voltages about what I'm being is displayed here, but we want to also minimize how you will induce, even in gold surfaces, corrosion on your surface, because you will have a higher electrical resistance. So you want to be wise. You need to be wise to select also your voltage range. So we take, for example, this sodium family, sodium dodecyl sulfate. We apply different electric potentials here, and then we saw nothing. And meaning open loop means when you don't control that electrical potential, but then it just behaves the same. You might see slightly some changes in the HTC, but that's in a very narrow heat flux. But if you zoom in, yes, that's a big change. But if you look at the wide scope of what's happening in the whole boiling curve, there is no major change. Same for the C2 min. Just to give you an example here, we have this different surfactant that we apply electric potential. So in a few words, the electric field does not induce considerable or it has negligible impact in the boiling performance. So now we have to describe this thing of like, okay, it has to be something to do with the cationions. It's not deposition because we were actually controlling the absorption mechanism. So, well, testing all these surfactants, we don't have any evidence that CHF should increase. Remember, we have 9 different surfactants, surfactants of different types, surfactants of different chain lengths, and all behave in a way that CHF doesn't increase. We have evidence that CHF decreases and the HGC increases. And if we look at bubble visualization now here, if we look at the C2 meme, who has this surfactant has a very extremely high CMC surfactant, the bubble formation of this one and also S2S, also another high CMC surfactant, it's so similar to water. So why you should be expecting that CHF should be increasing? We tested that whether it was the cation part, and we also have experimental data showing that CHF does increases, and also we provide bubble visualization that you don't see any major changes with those surfactants. So splitting this plot, because it's a little crowded because there are so many surfactants, now we split them by their surfactant type. Now we look at the cation, the positively charged surfactants, and we see that I'm not increasing the concentration in this one, but what is changing here is the chain length. So as you increase the chain length, because their CMC is closer to the testable molar concentration we tested, so we start seeing something that might be corresponding, whether if it's an equilibrium, sorry, I jumped that one, might be an equilibrium limited behavior because these surfactants, these extremely high CMC surfactants, reach an equilibrium so rapidly that it's faster than the bubble lifetime of 20 milliseconds. But if you have surfactants such as sodium double-silyl sulfate, which has a CMC close to the testable molar concentration, they are diffusion limited, meaning that diffusion, the bubble lifetime, they are limited by the bubble lifetime of, they are diffusion transport limited. So to explain this, we also plotted the surface concentration. So here I'm not plotting molar concentration, but I'm plotting the bubble lifetime. A different bubble lifetime from when it starts growing to the typical bubble lifetime of 12 milliseconds. And with that time window, we see that at these same concentrations, we see that yes, in fact, there's a higher surface concentration, but for the extremely high CMC surfactants, there's no change. Surfactants are not absorbing the interface. Just that's happening for the other type of the surfactants of the longer chain length surfactants. So this is inducing changes in the surface tension, which is governing surface tension is in fact governing changes in boiling behavior. Either it's an equilibrium limited behavior for extremely high CMC surfactants or surfactants that have very short chain length, or surfactants that might be diffusion limited for surfactants that have a higher chain length. Okay, this is a lot of information to process. So let's take our boiling results of the HTC and CHF, surface concentration, and dynamic surface tension. Let's plug them together and see if we can unify these results. I want to show you the groundbreaking work here from objective number 3. General correlations that can quantify boiling heat transfer for any type of surfactant. We have put in this master plot here where we have the RHTC and the RHCHF with the relative dynamic absorption and the dynamic surface tension. From what you see from our experimental data, putting all these, if you see very small these names, that's just the name of the surfactants, but what I want to emphasize here are the correlations, how they are very well aligned here. Putting all these vastly different, it's very condensed sort of research here where we have several surfactants and they follow this trend, this correlation where there is an increase in the dynamic absorption, and because of that increase in the dynamic absorption, that's inducing better volume heat transfer performance, and because of that, that's resulting in a decrease in the dynamic surface tension, and because of that, sorry, I repeated myself so many times. Because of that, you see the increase in the RHTC. So now, what happens to the CHF? Because of higher dynamic absorption, you should be expecting that your CHF should be dropping. And in the dynamic surface tension, the dynamic surface tension is decreasing, so that's inducing that results in the CHF. Highlighting two important correlations. The surface tension. Why I want to highlight these ones? Because the importance here of these correlations, they might look simple by looking at these linear feeds, but remember, this is a accumulation of a knowledge about almost 5 years in the making. And what I want to emphasize here is how important are these correlations. To give you an example, let's say if we use these correlations and we have a conventional tensiometer, we should be able to predict the boiling behavior or the boiling performance of any surfactant. A surfactant perhaps we have never tested, and you don't actually need to conduct the boiling experiments, but you can take the surface tension, you can take the surface tension of that solution, of that aqueous solution, and plug in your values with these correlations. And voila, you get your predicted results. To give you an example, let's look at the scenario number 1, where we have someone who knows that the HTC of water, it's in some order of magnitude. You can take it from books. There's a lot of reference where you know the HTC of water. And let's say now you add a surfactant. You add surfactant in boiling water. You take a commercial tensiometer and you measure surface tension, and you get some number, right? Some quantity. And for a typical bubble lifetime of 20 milliseconds. Question here is, what is the new HTC when the surfactant has been added? Taking one of those beautiful and powerful correlations of the RHTC, we plug in our values and we get that the RHTC has increased 1.5 times compared to the water. Isn't that powerful? What about the CHF? Similar cases, we take our boiling conditions, we take the surface tension, we have a molar lifetime. What is the new CHF when the surfactant has been added? Plotting these different correlations for the RCHF, we plug in values inside of that correlation, and we have that from the 1,000 watts per square meter that we have initially, that has been going down to 630. So you see, the powerful thing about these correlations is that if you haven't even actually tested a surfactant in your, it could be an industrial process, but you want to know, or you want to predict how that will respond to your system, you can take these correlations and predict those boiling changes. With this, I would like to summarize objective number 3 by stating that the applied electric fields that we test in our boiling conditions do not have any major impact for ionic surfactants. That surfactants that, regardless of their type, comply with this HTC-CHF trade-off behavior. When you increase the molar concentration, HTC should increase and the CHF should decrease. And we presented that boiling heat transfer for aqueous surfactants can be quantified with these powerful general correlations for any type of surfactant. Now, putting everything together as a closing remarks of this dissertation work, I want just to briefly summarize that in objective number 1, we explore a wide more concentration range, and we identify that there exists a unified universal concentration range that you should be expecting between 1 to 10 millimoles per meter cube. Now we have objective number 2, where essentially we have that changes in boiling behavior are dictated or governed by the diffusion timescale of surfactants, and you should expect that increments in the concentration are the boiling behavior synchronous to those increments in the concentration. And in objective number 3, we presented that these powerful general correlations that can quantify boiling behavior for aqueous surfactants of any type. With this, I would like to suggest future directions into this work, which is very fascinating and very dynamic, and perhaps this will give some guidance for future engineers that also want to implement surfactants in their boiling applications. We want to validate whether this transport limited mechanism for other conditions, such as whether if your boiling process is operating in high pressures, in positive pressures, or even in vacuum. We want to see, we have the theory how we can calculate that, we work to the equation, but we want to see if this will comply with experimental data. And also evaluate alternative isotherms. In my study, I have used the Lehman isotherms. I would like to see very much if different isotherms also comply to changes how we quantify surface concentration. And another interesting avenue that it's being actively explored by different groups is to record boiling behavior of aqueous surfactants with infrared camera, which it might be positioned at the bottom and synchronized with a side view camera, where you can visualize not only what's happening on the side, on the surface, but you can see the footprint of those bubbles. So we need to explore what's, we know this groundbreaking work. We have this beautiful information of what's happening with surfactants. We can explain what's happening, but we want to see if this can be generalized over all the surface. If what we are seeing on the side or in one layer, it's happening across all the surface that it's diffusing heat, and to also see how bubbles form. And of course, I would like to acknowledge my committee members, specifically Dr. Cho for all these years, for hosting me in the Kind Lab. It has been a beautiful journey working with Jeremy. I knew I have some background of boiling, but I wanted to get really into surfactants, and I knew he was the right person to approach to get into this field. My committee members, thank you for your patience. I was sometimes disrupting you during your working hours. I will just come to your office without any short notice, and I will just show up, but you will always have a piece of advice for me, and I really thank you for your time and generosity through all these years. And the machine shop, of course, we are very proud that we design all the equipment in the Kind Lab. That's something that I'm very proud that everything is built in here at UNLV, but also machine. We don't rely on or we haven't relied on external sources to get these systems. So there's a lot of learning opportunities here at UNLV, not only for us, but also for the staff that is at UNLV, because these are very challenging projects that need very precise machining. So they have been fantastic. So I really thank them. And the lead library and the GPSA, I spent countless hours. If I wasn't in the lab, I will be in the library. And I think UNLV has vast amounts of resources that allocated me the comfort to conduct my research, and just sometimes to change the scenario, I will go to the library. And GPSA has been very supportive, financing either some of my conference trips, or for any other suggestions that might be for graduation or things of that. They will just give me a piece of advice. This work has been funded by different sources. I also thank these, all these agencies for trusting in us and also allowing us to do this beautiful research. And well, I'm showing here a single picture, but remember, I knew that people is important in my research, but I was submerged, living in the lab, staring to this equipment, but I always knew that we need people. People are the driving force to keep doing what we do. I'm really thankful to all the lab members who have been, if I'm missing someone, please excuse me. There were so many pictures I was going through, but people are who really makes this very special. People at Dakine, well, if we were in Dakine, with people from outside, people who is present here or might not be here, I really thank them for their time and their friendship. I also, people think like I have a couple of family friends and they think like I'm just in Las Vegas, like I have plenty of time just to go notice to their schedule, but which in fact I really enjoy, because I always like to play the tourist and go to the street or somewhere else. But then I have people visiting me and saying, "Hey Mario, do you have time for tonight?" I'm like, "Yeah, I'm doing research." It's kind of difficult to explain what we are doing here. Or they also sometimes will question, "Are you actually in the lab?" Well, I can explain you what's happening. And I have a couple of friends. I'll be missing some of them as well here. But I want to show you that in my free time, I really enjoy cycling. I have my buddy, Ken, who has been, I will just get lost in Las Vegas, even during the scorching summer. So if I'm not doing boiling, I'm cycling. And that's basically the two driving force that keeps me, on track of, of what I do.
That's all selfie.
Yeah. And the interesting thing, I don't have social media, so people ask me, when are you gonna post this? I was like, I don't have, I just gonna send you the pictures. So, I just like to take pictures. So my family, of course, they have visited me here for a couple of times. My sister, my mom, and my dad. Yeah, I've been far from my house. From home since 2010. I've been going to different places, and being closer is very special because they can visit me or I can go. But in fact, actually, that's not that easy because we don't have direct flights. But still, we have, at least I'm closer to them, but also I feel them, they are closer to me. And I really thank them. Thank you, Mom. Thank you, Dad. My sister. Thank you very much for that. I have some pictures with them here. Yeah, this is my sister. And of course, we always talk about our animals, right? Our mascots, my dog. I really miss my little dog here. I have my niece and my nephew. And yeah, that's, I do this thanks to them. They are my inspiration. And well, this is the end of my presentation. I would like to close my presentation here and open, for Q&A if you have any questions or suggestions that out of this work. Thank you. Thank you for being there.
All right, so we'll do questions from the audience and also open to the committee as well too.
First question, Mario. Can you do one more selfie for?
Yes, I can do that. I will be so honored to do this selfie here.
Secondly, in slide 44, I wanted to ask a question about something here. You're speaking of your graphics here, like your attention to the uniformity of your graphics and presentations throughout this whole thing is like a big part of what made this more understandable. So that's really awesome. Like, I know you pay a lot of attention to generating those graphics. I'm sure a lot of Illustrator and other, all the various softwares you need to get this right. It's a lot of work, so it's probably 100 hours that you spent on that at least, so good job.
Thank you, Blake. I really appreciate it. And I learned so much from your work that I'm so happy having someone else doing similar work that your work was also an inspiration for us to have, the first designs. And yeah, I really thank you.
Yeah, it can be a lonely road, so it's good to have some companionship there. I was curious in this plot, we see on the right side goodness of fit of these this kind of like first correlation that you've produced here to this dynamic surface tension is pretty good. And then on the left, we see a bit more spread here with just a stab in the dark linear fit to the data for the relative dynamic adsorption correlation. And I'm curious where you think that predictive power, where there's more spread there, and is that perhaps, do you suspect that that's due to difficulty in the empirical data, or the choice of the isotherm, or some other factor that makes that less tightly correlated choice there on the left-hand side?
That's actually a good question, Blake, and thank you for pointing that out. So if you look at this, the dynamic absorption here, the way how we quantify might be very, as you mentioned, maybe how we express that with the isotherm. But what we see here, this is CHF, and you see that for all these surfactants, we keep testing different surfactants to have a better fit, but not only to have a better fit, but to see if they will comply. And we could keep testing perhaps another 30 different surfactants, and we are very confident that will go align this correlation. I think that there might be, there's room always for improvement, so we can have a better fit, and that will depend also this interplay of if you are diffusion limited or equilibrium limited, and the concentration, and also how well consistent are your boiling results, which also we are very, very confident about that, because we have, in the background material, I could explain you that. To address your question, why this spread in the dynamic absorption maybe might seemingly look a little more open, I think it's just the way how we have also you see the range we have, because of also the dynamic absorption, we have a tighter range.
Yeah.
But if I change the range, I should be expecting also, a slight change here. Yeah. So we are covering a larger range with the dynamic absorption.
Yeah. Just to piggyback off of Blake's question there, you expect the behavior of bubbles, right, in boiling. You think that they would more tightly correlate with adsorption, like the number of molecules that absorb there, or to the more macroscopic property of surface tension?
I think it has these specifically in this objective. I wanted to emphasize that boiling is highly dictated by changes in the surface tension. So it's very tight with the changes in the surface tension. So that's why we might also see a tighter fit here, whereas the surface dynamic absorption comes because of those changes in surface tension.
Is there a direct correlation to these two, dynamic absorption and the surface tension? I think they showed, right?
Yes, exactly. We saw that for example, in this plot, we see that the changes in here, as we increase, how surfactants, the amount of surfactants diffused in 3D interfaces are affecting the surface tension. But surface tension is the one that dictates how boiling behavior should occur.
I have a question for that slide too. So some of them are arrow bars, some of you don't have arrow bars. So some arrow bars are really big, some you don't. What's the reason?
And Dr. Cho, Jeremy also asked me that when he first saw this, he's like, oh, you're missing the arrow bars. In fact, the arrow bars are there, but the error bar of this
Small.
CHF is too small.
I see.
For when we plot the RHTC, we in fact, the way how it's quantified, if you remember, we have heat flux over temperature. But here we are taking the maximum heat flux. So that change between experiment to experiment is very minimal.
The dots is too big.
Exactly for visualization purposes.
Another question. So I assume like if the surface tension changed, the bubble time should like surface tension, the bubble will leave quicker. You see that? You see all the bubble change like 20 milliseconds.
Oh, okay. So this is an interesting question because as you are increasing the molar concentration, bubbles are becoming smaller. And because they are becoming smaller at higher concentrations, that will correlate to changes in the bubble life.
So in terms of bubble detach time, it's like a kind of like a constant, like 20 milliseconds.
Exactly, but which we could easily, take a different value, let's say 10 milliseconds. And we saw even when we plotted 1 milliseconds, that shift is slightly, even, like 10 times smaller, we still see the similar behavior. So that's a really good point. Yes, in fact, the bubble lifetime might be oscillating, but it's still in the same order of magnitude.
We apply electric field. Have you tried AC field or you try DC?
We apply DC field.
Yeah, because what's happening is that if you apply DC, you form double layer. Double layer will scream out all the electric field outside, like usually double layer signal is like 10 nanometer. So outside 10 nanometer, you won't see any electric field. If you apply electric field, AC field, the electric field will penetrate into the ball. High electric force to make the bubble quicker or slower. At DC field, it's not surprising that you don't see a difference because the double layer screen lines.
Thank you for the observation. Perhaps it's something that anytime after, like I can test to quickly.
Try AC and see what's happening.
What kind of frequency?
Frequency depends. Like if you can go to like if you don't want any like electrical reaction happen, then probably go to like kilohertz. You should be able to see something happen. Yeah. Try that. See. Quick try. Oh, also another question is, I guess you build a smaller boiler and then you make a bigger boiler. Like, what's the reason you need a bigger boiler?
So basically, it's Dr. Cho, a way to keep me busy in the lab. So, pandemic, right? It started and we started building our first equipments in the lab. And we were designing the big boiler, but that will have it took us almost a year and a half just to have it. So in that period of time, I needed to conduct research, right? So we have this small boiler, and because in my master's, I did boiling heat transfer, and of course, combined with all the knowledge of Jeremy, we wanted to have a quick way to explore objective number one.
I saw that you so you want to make a build bigger, but
yes, exactly.
I saw that way.
Well, thanks to the small one, we were not testing the unknown in the big one because operating the big one just takes. If you ask Blake, which has a big boiler as well, we have to deal with a lot of challenges. And so I'm so happy that Dr. Cho guided me into testing, starting with the small boiler, which at that time I will complain how long it takes to conduct the experiments. But once I transitioned to the big boiler, yes, it was.
The volume in both small versus big are roughly comparable, but a lot of the additional size and complexity of that big boiler, I believe, is it just you guys are working on maintaining your boundary conditions, and like it's not about more water, it's about more control over that volume, right? And that's a big part of the complexity there.
Exactly, to have a more controlled system, and also because the operating range, we need to do it in a safely manner as well. And we could have reached CHF with the mini boiler, but we might encounter some situations that wasn't suitable for that. But with the big boiler, we can do the experiments that we actually wanted to get into.
Did you get to starting a fire in the lab?
There were some instances.
I got smoke at one point. My control routine stopped telling the heater to lower its power when a set point was hit, and I knew something was wrong. I smelled smoke. That rapid disconnect in your heater block and your copper block is a big part of, I think, the safety feature there.
Yes, that's in fact, the big boiler was, that's another big difference. The big boiler was, I would say, fully automated, but there was a big intervention every 30 minutes, which kind of, well, I needed to disconnect that block. Otherwise, if you remember the different boiling regimes, then after CHF, we will rapidly transition. There's a small decrease in heat flux, but then that difference in temperature will just spike. But that once occur, how do you stop that? You can inject some cold water, or like a coolant, but we do not have that. We need to adapt the boiling a different way. So an easy approach for us was just to cut off the power supply or the heat source, and then by natural convection, we'll just cool down.
We owe that design to you guys.
Exactly. So that's why I love
Well, you guys have it, like when I have to disconnect, I have the scissor lift and the thread gets stuck. So I had to just like push the scissor lift down because your rapid disconnect, you can just do a dead man switch and it just drops.
We thought about that approach as well. Yeah.
So I've seen the refinement in your design choices. There's a lot of thought went into that. So good job.
Thank you.
Any other questions?
Just a short question. It's not very like technical or anything, but on the slide where you had all the plots of the different like the effects of the electric fields, I noticed most of the plots were the same, but there was one curve that was very different than all the rest. What is going on there?
The open loop, the green, that's for the sodium dose.
Yeah, the
You mean
plot.
this one, right?
Yeah, the DIW plot.
You mean this one?
Yeah.
Oh, okay. DI water here is for reference. There is no surfactant there. So when these ones, actually, you just pointed out something. I did not mention here what was the concentration. So yes, so this is DI water, and these other plots are tested at 5 moles per mercury. So because of that, you know, absorption to the interfaces, you are changing HTC, so you see that shift. And there's a minimal change here in open loop, but that's just as also Jeremy has investigated in previous work. There's he can tune that control with the electric field, but that's occurring in a very narrow heat flux range. Questions? Yes or no?
Mario, thank you so much for your presentation. It's great to see you up here finally defending. As Blake said, I'd like to default his statement and say that, yeah, your visuals your graphics are beautiful, and even this data here is beautiful. I had a few questions about some of your plots. If you could go back to slide 31, please.
31. Okay, this one.
Yeah, so my question was with plot B in this. So are those tails uncertainties with your data exactly? And if so, why are those so large? Did you expect this? Is this standard with this type of research?
This goes towards the similar question that Charles asked, if whether there's uncertainty here. Well, these are plotted with bands instead of like bars here. So you see here also the range, right? You are looking that we are plotting this, the HTC, but if you look at this range, but this range, it's very covering in a range that is very narrow. So we have the heat flux, which has some uncertainty, but also we have the difference in the temperature. But for the critical heat flux, what we are taking here it's the heat flux itself. So we are, dealing with, less uncertainty also happening in the boiling results, but also the float range, it's wide open here.
Because the HTC being a function of a delta T, there's a more sensitive parameter that leads to higher relative uncertainty in that middle plot. And is your intent here that you're showing that these are roughly indistinguishable from one another, so you're not necessarily trying to separate them, like, is that kind of the intent here in plot B? And it's okay that these curves kind of are all in next to each other, that's an implication that this is not about the choice of surfactant, right? Kind of
Yes, the point I wanted to make here is that these changes are synchronous, something that we didn't know before. Why is CHF changing? It's because dynamic absorption. Why is exactly HTC changing? Because dynamic absorption. But very interestingly, they also happen very synchronous here. And that's because there's a faster diffusion rate occurring, which is, that's the reason I wanted to plot these things together.
I think the question was more about like statistics, right? About like here in this case, are you trying to emphasize the actual spread of the data or the movement of the means, right? I think it's more of the latter, right? To say that the movement of the means, while there is a large spread, the movements of the means seem to be synchronous, right?
Yes, exactly.
And I think I understand this a little bit more. So you're looking mainly at the shape of those curves, right? And correlating HTC to CHF, if I'm understanding correctly. Okay, so my other question is with plot C. Is this representing more than 4 data points per line? Because I had a concern about the fitting that you're representing in this curve here. I just want to clarify that.
Okay, so these were the same concentrations. We have, well, I'm plotting here, we have a very low concentration to 10 to the minus 3 here, moles per meter cube. So if we pick the 4 different concentrations, we have this one, this up to 1 millimoles per meter cube. And similarly for the HTC, they were same concentrations, but these are from the same experiments itself.
4 experiments per curve, and then in between it's like a spline fit for this, like a qualitative fit to that data.
So every concentration, there are 3 experiments, and we have 3 different surfactants and 4 different concentrations. So there's a lot of data here.
Yeah.
Yes, it's a lot of data.
But I guess my concern was with how you fitted your spline in TW40. It seems to suggest that there is an increase in the critical heat flux between those points. Where my question is, are you sure that's representative of that relation? And if not, could there be more experimental work between those 2 concentrations just to clarify that relation?
Oh, I see your point. So your concern is whether
It's like whether that line is true, the line that's drawn there.
yes, that's in the first objective number 1. To be honest, I presented that we have tested between 10 to 12 different concentrations, but in fact, in our exploratory phase, we tested like close to 20 different concentrations. So we are very confident how that train should be behaving.
When he's talking about that curve in the blue line, which is, it doesn't mean anything, it's just how you drew the line.
Yes, so if this is just in a way how I plotted in the Wolfram Mathematica, instead of having like, for example, like a straight line joining these 2 points, then there's an
Or I see you some data fitting, fit the curve, right?
Exactly, but if we remove that fitting, if we just plot like a straight line, you should be expecting, the same.
I think he make good point, like, I don't think you should draw perfect, because that's kind of confusing, because.
Yeah, it can be misleading, yeah.
I would suggest you just.
I can do that.
Because then, his question is, you see there, Compared to other one, you keep decreasing, this one starting increasing.
Yeah, it can look like a model, right? It could like, what equation are you fitting to that? Yeah.
So that's confusing.
Unless I explicitly explain what was the fit point, yes.
I know, but then people.
But it's not a fit, it's a.
It's not fitting.
Yes.
Maybe sufficient to omit the line even and be more clear about this, because when you omit the line, you might lose some distinguishing of the symbols, but like make the symbols larger and omit the line, and you might end up with a potentially less misleading in this particular case.
But you could very clearly say, right, like the like splines are drawn for visual aid, right, but they don't represent.
And we can
data,
provide
right?
that, yeah, the actual, okay, for illustration purposes of.
If that's the case, I also noticed that same spline fitting in slide 32 as well, when you compare your data to your collaborators' data.
Yes,
I
exactly.
just wanted to point that out as well.
Yes, we took a similar approach in that fitting, which will, we could, follow that suggestion and just, fit that with straight lines and say, okay, we have this, and we can also, for simplicity of visualization, we can show this, but the actual, train of that data, it's, we can do the linear. Thank you, Donald.
Yeah, thank you, much
I appreciate
appreciated.
that.
Well, in the interest of time, I'm going to close off the general audience portion of this, and then it'll just be committee members. And Mario, stick around.
Very good work.
Tell my stuff.
Example for other students.
We have also Dr. Kim here.
And he can ask a question after they leave. Yeah, I think
No, we'll just wait and see.
when you show data. Starting soon.
Oh.
Something like
Good job. What are you?
kind of like go straight line, tell people.
In conferences, we have shown these straight lines.
And they say you needed to show most.
And we have these straight lines, and then for this paper, we could supply like these straight lines.
You can using fading, but you should not change the data trend, you know what I mean? Because if you think, oh, something is changing.
That's true. Sorry, I just want to ask you what's next here, because we might still have
People ask you questions.
Yes, exactly.
Oh, okay, yeah, can you just make sure that anybody's not.
So I have to ask them, where is
You.
Yeah.
All right,
You can kick them out.
thank you everyone for who is here in Zoom, my friends and probably family already left as well. So now I will leave this just for my committee members. So I will ask you if you could, maybe we can chat after that, and then I will talk to the committee members with Dr. Kim here, and Dr. Melissa Morris still might be here.
I'm here. You hear me?
We'll just basically leave the Zoom because I have a closed session with my committee members. Thank you. I think I can.
Yeah.
Okay.
Yeah.
Adiós, Ana. Gracias. Shani, Anna, Angel, and would you please leave the Zoom?
Try to put it in here.
Okay, perfect. That was actually a good point of Donald.
Okay, all right, okay, Dr. Kim, we are all, it's just us.
You hear me?
Yes.
Yeah, it's excellent work, Mario. Excellent.
Thank
Okay.
you. I appreciate it. Thank you.
I wish I have a student like you. Okay. Okay, so I have just few questions. Just comments. So basically, selection of your surfactant, those are linear molecules, right?
So your question is if the selection of the surfactants is something that would
Linear shapes, right? So that's you can make a comparison.
Linear
with
tails.
linear tails, basically, right?
yes, I mean the tail length is compromised by carbon groups, so it's depending on how many carbons are in the tail, that will depend the size of the tail.
He's asking like you don't have branched surfactants or.
Oh, there are no branches. Yeah, there are no branches on the tail. Yeah, just
Yeah.
carbons.
Yeah, so that head shape is pretty much the same. So any comments on that? So what if you have a branch surfactant, like for example, non-ionic, there's a group of surfactants that actually works pretty well. In other words, the size of molecules can be a little bit smaller, but they can maybe move faster, so that diffusivity side of it, maybe some advantages, stuff like that. But I think those things can be captured in your time scale, right? At the end, right?
Yes, exactly. Depending on we have seen like at least for the head size, if we compare surfactants, or at least to my knowledge, yes, surfactants will change in head size, but we shouldn't be expecting a major change in the head. For example, now we have the ionic liquid base surfactants that they have the cation, which also the sodium sulfate, they have the sulfate part. That might change slightly the oversize of the head size. But most literature, what I've seen, like has been focusing, or recent literature of the tail length. How is the tail length affecting that? Which I introduced here in number 3. So I think it could be an interesting avenue to explore whether the head size can also correspond to maybe significant changes in diffusivity, or if we can picture the same results with that.
Yeah, okay. I just wanted to make a small comments on that. Or maybe sometime later, you can have a very large scale charges as you're trying to do something more like an ionic liquid type of things. Some of the ionic liquid actually move very, very slowly. So, I think you're trying to explore that. So that's very good. And the other thing is, it's nothing to do with the boiling. The interesting thing is actually, you are studying, behavior of surfactants for boiler, basically, right? But if you look at the systematic approach, yeah, maybe surfactant can enhance the heat transfer or something in your boiler side of it, but there is also a possibility that not work as good as maybe condenser side of it. Is this, you understand what I'm saying? And also if you deal with maybe high salt solution like a lithium bromide or something, you're talking about absorber type of thing. So maybe, at the end of the day, you might want to ask yourself, systematic point of view. Okay, you've been selecting some of these surfactants, how they will also cascade into other type of, systematic, heat exchangers, something like that. Just my comments, you know what I mean? So
I totally agree with you, Dr. Kim, because all these years for me, like actually thinking, okay, who is actually using surfactants in industry, and are there like just like going these surfactants like and unknown quantity until they see some changes in foamability, perhaps. Maybe they want a very more like a foamy agent. But I think like surfactants are also widely employed in some other applications where the contribution in boiling heat transfer can be translated as well in some other major fields like condensation, but which of course I haven't tested myself, but I should be expecting that formation and changes in wearability perhaps will be highly depending on the concentration itself. And now people kind of like just testing on the fly and guessing, okay, now I see some change, but now we can direct and tell people, okay, I think you should be looking into this and these timescales, you know, and concentrations. So I think it can open new doors to opportunities in current research, and also maybe future technologies might be depending not on boiling, but in a two-phase process such as condensation as well.
You also mentioned Addison's project.
And yes, and Dr. Cho has been guiding another one of our students who is looking into formability, or he was doing another side project as the firefighting, you know, to mitigate the fire. You know, the firefighters use these foaming agents. So also that's concentration dependent. That's no boiling, but also that's how can we, you know, measure that formability, which people has been, you know, like quantifying, or maybe we can insert our new knowledge into those fields as well.
Sure, good. And you know, since you brought it up, I think it's industry some years ago, particularly for absorption industry, the main reason that they start to use surfactant in their system was because, for example, you know, lithium bromide or lithium chloride, those kind of solutions, those are very high surface tension, you know, relative to water. So as you point out, they wanted to deal with just spread out the fluid on their machine. So then they start to figure out, hey, there's some other things are going on. So eventually, and turns out to be a very good thing for them to actually put those surfactants into their system. But they also knew that once you put those surfactants, you cannot take it out. So but they took the risk, and it was pretty interesting actually, if you look at the history of it. So
that's really interesting, Dr. Kim. And also, as you just pointed out, once you put surfactants, if you need to clean your system and swap, let's say, the fluid for, let's say, a new fluid, since, you know, there is a considerable reduction in surface tension, that fluid will impregnate into very small cavities that when you flush water, for example, you might not be able to remove those residues. So I see kind of like why maybe some in industry might be kind of skeptical, like, oh, I think like maybe the surfactants will ruin our system, or how can we clean it? And yeah, I can see also those concerns.
Yeah, another thing that I can make a point is there's a lot of fluid that they also create a lot of corrosions. So one time we were interested in developing just one chemicals can do both. In other words, anti-corrosion as well as, you know, heat transfer. I think it's still valid approach. You know, I don't have time to do those kind of things, but maybe Maria, you can explore that later sometime in your career. But just
that sounds very interesting as well, like the avenue. I've been trying to think like how out of my box of boiling, how surfactants actually can be implemented, and by looking how Jeremy has been guiding different projects with, you know, with the timescales and how diffusion can be, you know, explored. I can see big potential projects as well, you know, with this knowledge that we, you know, bring in here.
Yeah, that's it. I also try to sell surfactant industry, but they don't seem to take it well.
Yeah, it's these fields tend to be really stubborn. But no, I didn't know about the lithium bromide, lithium chloride stuff. So yeah, I'll have to chat with you on that. All right, so at this point, Mara, let's end this, and then stop the recording, and then, or you can stop the recording right now.
Yes.
And then, we'll have you leave the room.
We just close everything.
Stop recording.
And I might have that camera running. Oh,
that's
what
fine.
about Dr. Kim?
Oh, keep the Zoom on, but then stop the
okay.
recording. Yeah.
Okay, so.
He's the one you hear what we say.
It's very secret.
By the way, you make this iced coffee or you bought it from Starbucks? Iced coffee.
That one is from Panera, and they suggested that we put ice, and then I have Guatemalan coffee on the other one.
Brewed your own
Okay.
ice.
Yes, yes,
Great.
kind of like tasting a little. Sorry, this is stop. Okay, I will stop the
Stop
recording.
recording. Stop recording.
There you go.